Professor,
Hello, guys. Yeah.
I have a question.
Mm-hmm.
Well, hold on. Normally, when we classify the labels, the threshold value is 0.5, right? We do not need to.
Yeah, depends on the labels that you choose in the in the training set. Depends on the value that you assign to the y variables. We typically use 0 and 1. So the middle point between the two labels is the threshold to use.
Oh, I see. Okay, so if we use 0 and 1 as the label, so the threshold is automatically is 0.5.
It's assumed to be, yes.
Okay.
The model assumes. Yeah.
Oh, I got you. And another problem I got is another file is 4 more materials, and it asks us to install the TensorFlow.
Right.
But, yeah, I tried to install it, but it asked me you may need to restart the kernel to use updated packages.
Did you get the message in Jupyter Notebook?
Yeah. Before this message, I got another one. It's like you need to update your pipe and something.
Okay.
So
happy. Both of these are standard message. So for Pipey, it's less of an issue.
Mm-hmm.
For the kernel, the only thing you need to do is save the Jupyter Notebook.
Okay.
And close it. Mm-hmm. Close that Jupyter Notebook and maybe also close the session. So completely log off and close, okay. And then start a new Jupyter Notebook session. Okay. Mm-hmm. And by then, if TensorFlow is installed correctly, you can use like TensorFlow. You don't have to install it again.
Mm-hmm.
Yeah.
Okay, I'll do this. I think I did this the same way, but it sounds like it haven't successfully installed. Okay.
So if you are going to exit Jupyter Notebook anyways, you might want to just install the package in prompt.
Oh, okay.
Right, if you won't exit anyway.
Okay, I got you.
Right. So, but this is not related to the homework, right? This is the in-class demo.
Yeah.
Mm-hmm.
Professor?
Yeah?
I have another question related to the homework, and it is also related to Elaine's question. So in the homework, it asks us to classify the labels using threshold 0.5.
Yeah.
But since we are using the argmax function, do we still need to use the threshold?
Let's see. Which question is this?
Let me see. Is
I think this is
question 7.
Question at end of question 7.
Yeah.
Okay, let's see. This may be something that I ignored. Question 7. Let's see. Oh, so in one of the steps. So it's the accuracy. Okay. Classify labels using threshold value 0.5. Right. Yeah. Hold on. Oh, right. argmax. You're using argmax, right? Right. Right. You should use argmax. So ignore the threshold value requirement.
Okay.
Yeah, just use argmax. Yeah. You all got that, everybody? This is about one of the questions in homework. It's the step-by-step neural network implementation. One of the steps is to make predictions and calculate the accuracy. The requirement asks you to use a threshold value of 0.5. You will not use that. You will follow the tutorial, and you will use argmax, right? So disregard the requirement about 0.5 threshold value. That's it. Any questions? Let me know. So because it's quite clear, I'm not going to update because you're all halfway through the questions. There's no point to update the homework file. So we just know this based on this course, based on today's meeting. And so I will not update the Jupyter Notebook file. Let me know if you have any questions. All right, how are you guys doing? I guess it's winter. And the winter today, maybe next week is summer again. I'm used to this. So who likes winter than summer? Nobody? Winter?
I prefer winter over summer.
Yeah. Mm-hmm. The place that you came from, do you have winter more than summer?
No, like in India, it's hotter over there. So like I prefer winter because at least like I don't have to deal with the entire heat and humidity. So winter is better in my opinion.
Yeah. Well, I guess you like your bed very much in winter. You can
Yeah.
go in your bed all day, which is fun. Right. Okay. Who else have questions about homework? We can plan for some time in the end of today's meeting, but I'd like to get a sense of how many questions you have. If not, then great. We won't use all the time for today's content. Let's see. So are you pairing up? Do you use the study pal? I mean, or do you discuss anything with your study pal? Excuse me? Oh, sorry. Oh, anyway, so my question is, do study pals come together? Do you know about that? You don't know about who your study pal is?
Me and Elaine has discussed some questions.
Okay, so you can see who your study pal is, right, in Blackboard?
Yeah, I can.
Okay, great. Now you can also send email. You can use the email function in Blackboard. So as long as you know who your study pal is, I think that will be the basis for group project. So I'm thinking about 2 students will be a good group size, because this is more, the way this is more coding based. So smaller groups will be better even. Right. Does anybody have anything to complain about your study pal? No? All right, great. Then we'll move forward. And homework 3 is due this weekend. Today's content will not be in homework 3, but it will be in homework 4 as well as in the final. And in general, in a predictive analytics project. So in the final final group project, you will discuss some of these. And there are a lot of terms here we'll talk about, and it can go deep. So it can also be confusing. But these topics will be very helpful. What I find is, I go to those data competition website, Kaggle, and other things. Kaggle is the most popular website. The other is there's a UCI data repository. I also use that a lot. What I found is many enthusiasts, many analytics enthusiasts, most of them are amateur analysts, they have fun, which is great. But based on the way they discuss their results and discuss the issues with the data set, you kind of have a feeling that the majority of them do not know much about that. They know programming, they know how to solve some problems, they know how to make a prediction, how to train a model, how to get those mostly accuracy scores, but they can also get F1 score, which we'll talk about today. They can get mostly it for estimation problems. They will get the R squared, or not R squared, I mean square error, and other metrics. They know about these mostly at surface level, but something that don't get discussed, but a lot of times is critical to examining those, is the thing that we'll talk about today: false positive, false negative, false positive rate, false negative rate, recall, those concepts. We'll talk about those. They don't discuss it, and I think a lot of them are not aware of these terms even exist or is relevant. So a lot of times they are satisfied with the accuracy, and that's it. They stop there. When they see their accuracy rate is 85%, they feel happy. They think it's good. But you know what? The class labels are imbalanced. There are 15% positive cases, 85% negative cases. So by doing nothing, you randomly guess, or you predict negative for all the cases, you get 85% accuracy. So after all the work, they get a model that is doing nothing. So, and they didn't know that. So today's class will be sort of another step that you will differentiate with those self-learning, self-starters, who probably doesn't know the importance of the different kinds of evaluation scores and different kinds of classification errors. So, one thing that you have learned that differentiate yourself with those, let's say, amateur data analysts or data analytics enthusiasts, but self-starters, are that you know how the neural network model learns from data inside the black box. What's happening inside there. The second part is what we'll discuss today: model evaluations and decision analysis. This is particularly relevant and important to business projects and medical or healthcare projects, mostly predictive. So far, we have been focusing on predictive modeling. Today will be the last lecture about predictive analytics, beginning from next week, or hopefully, if I finish everything today, Then beginning next week, it will be a different animal, you know, unstructured data, textual data. Very exciting, the next phase of this course. So, you know, cherish the last class about the things that you're mostly familiar with, you know, predictive analytics. So let's see. I uploaded the slides a few hours ago. You may want to download those materials. I also uploaded the class demo Jupyter Notebook maybe 1 hour ago. You can download them. It's quick to run the Jupyter Notebook if after you download it if you want, but it's already run. All the results are preserved in the output, so you didn't have to run. Even if you run, you'll get the same results because of the random seed. Okay, I'm planning to use 1/2 hour today to talk about model evaluations. I will upload some more videos, maybe the rest of this week or maybe early next week, about the stuff that we'll talk about today, but may not have time to go too much deep into it. When I make videos, I can elaborate and use other, you know, visual cues to explain. So that ought to be good. And some of them will also be useful for homework. All right, so let's get started. Any questions before we start?
Professor, so
Yeah.
the blackboard say the homework 3 due for tomorrow is due the weekend or tomorrow?
Did I say tomorrow?
Yeah, October 29.
Let me, okay. I don't have it with me. Let's say tomorrow. Is tomorrow okay? If it's okay, then we'll stick to that. I think probably when I first scheduled, it was last Saturday, but I like to allow more time, so I extended for a week, but it didn't want to go too long. So maybe I put it on Thursday, so that you still have a chance to ask questions today, and you'll have time to finish it tomorrow. If tomorrow is okay, we'll stick to that. Is it okay?
I prefer Saturday only because I have project.
Okay. Anyway, this is a trade-off. It's not that everybody benefits the same. If deadline is farther away, you tend to, you know, postpone, but it will leave less time for you to do the fourth homework. You know, it's up to you. Why don't we do this? I'll keep the current deadline just so that some of you prefer it. But if you prefer Saturday, go ahead and delay it until the Saturday. So Saturday will be the hard deadline. Thursday will be the implicit deadline. You know, hopefully it works whichever you prefer to. There will be no penalty as long as you submit it by Saturday night. But the system will say by tomorrow night. Works? Okay.
Yes.
Yeah.
Thank you.
Great. So after you submit homework 3, you can start working on homework. I'll still have to upload it. Maybe I'll upload it in a couple of days. All right. Okay, so let's get started. I'll share my screen. Okay. You see it? Do you see the slides? Do you see my next screenshot?
Yes.
Yes, we can
Yeah.
see.
Great. Okay. Okay, model evaluations. These are the topics. at high level. So stop me anytime. I like to be more engaging and allow questions. Some of you are enrolled in the Capstone Project course. You have already read some highly specialized papers, academic papers on data science, predictive analytics. You have encountered some of these terms: F1, ROC, AUC, confusion matrix, and they don't talk about confusion matrix in the paper because everyone knows it if they read the paper. But by this, we mostly mean the rudimentary terms: true positive, false negative, false positive, and true negative. And mostly we'll use positive predictive value, negative predictive value, false positive rate, and false negative rate, as well as accuracy and errors. So in the process of me explaining these, whenever you have a question, let me know. Raise your hand, get my attention. I like to discuss these with you. I don't like to keep talking myself. I think if I keep talking, I make a mistake when I say something I didn't realize, because these things are very confusing. That's why they're called confusion matrix. They are confusing. It's better if we talk about it, and sometimes I'll realize if I said something wrong. Or if you catch anything that I say wrong, definitely let me know immediately. All right? Dio? Yeah? Okay. Now, conceptual topics. So here's a list of things. I just wrote some of these. The terms in bold, they are fundamental terms. Most of the other terms will make use of these elements. The four terms are what makes up the confusion matrix. We'll talk about that in a second. Things in black are those that we'll talk about. And these come in groups. These three are the error. These three are the rate, what we call the true rate. And we have some fancier terms. And there's a chart that it has some advantage of model evaluation, that it's robust to some factors that change from project to project, so you can compare across projects. These are standard evaluation metrics. Things that in gray are optional, although the calculation of one of these, actually these two are the same. They help calculate F1 score easier. So even though these are optional, but these are optional because we have too many terms here. I don't want to make it too overloading. But anyway, without these, you can still calculate that. You just need one more step. Okay, so that's the structure. To clear out a few key terms from the beginning. This is a confusion matrix. If you read about model evaluation and decision analysis by Googling, you must have seen different versions of the confusion matrix. They look somewhat similar, but sometimes they change the layout. You didn't realize the cells don't fall into the same concept. It gets confusing. So especially when you are learning, make sure you stick to the same format. if you see other formats that are slightly different from this format, you can change, you can adapt the format, the structure, and you can change it to something that you're familiar with. So a computer matrix, the main body of it has 4 cells. It's 2 by 2 conditions. So there are four combinations, 4 different combinations. These don't change, they're always 4 cells. But what are the columns and what are the rows? And what's the first column? What's the second column? What's the first row and second row? They change from different, different people display them or structure them differently. But typically they put predicate labels as the columns. So what does it mean? This is the Y-pred. After you have, and this is under the binary classification framework, you have 2 target labels. You get the Y-pred based on the activated score of the output unit, if it's logistic regression or neural networks, and you use either use argmax or use a threshold value to predict label. So that's the result, that's the outcome, or that's the output of your model. And some of these are correct, some of these are incorrect, right? These are not ground truth. The number of correct classification would depend on how well the model did. The rows are the ground truth. They are the true labels of the Y data, Y train or Y validation or Y test data, but not other sample data. You don't know. You don't know when you are trying to predict it. So, and I like to put the prediction as a columns and put the ground truth as the rows, so that I know. And I like to put the headers, the name of predicted labels on top instead of put it on the bottom. It changes the diagonal line. If it's on top and actual labels on the left, you have the diagonal line go this way. But if you switch the labels or headers to the bottom, the diagonal line changed direction. It totally changed the structure of the table. It changes how you use the table and interpret the results. So I don't like to do that. In Python, sometimes because of the way x-axes are on the bottom, sometimes this happens. So what I would do is to explicitly change the layout so that it's the way that I'm comfortable with. So based on this layout, I would assume that that when I say diagonal line, it's this line, and the 2 cells on the diagonal line is the true positive and true negative. Off diagonal line are these 2, and they are false predictions, so that it's clear. 2 labels, positive and negative label. I talked about this in the prep video. Hopefully you watched it. Did you watch it? I uploaded late yesterday, so excuse me for that. But if you watched it, you know where I'm going. Positive label, negative label, they don't mean good or bad. They just flag an event that is of a primary focus for the specific project. So we talk about default. In terms of default, credit card default, account default is a positive label. And the other outcome, which is healthy account or no default is a negative label. Account default is not desirable. It's something for the bank to catch, but doesn't matter. It's a positive label or positive account. In another case, customer churn. Churn is non-desirable, but it's a positive label. But in other cases, you have donation, and detecting a donor is a desirable outcome, but still that is the positive label, positive outcome, because that's a primary interest outcome. So we'll use P and N to denote the different outcome. P and N refers to the label of the customer or label of the event. Then you will use T and F, true and false. True and false refers to whether or not the prediction is correct. True means the prediction is correct. When you have the true, a positive case is classified as positive correctly. A negative case is classified as negative correctly. When you have false as a leading letter, it means something is wrong. And this is where things get confusing. You know, whenever you have the whenever you have the false, these two, whenever you have the false, the label, the second character refers to the prediction, but because it's false, the actual case is the flip side. So whenever you say false negative, it's actually referring to a positive case. It's a positive ground truth, which is incorrectly classified as negative. So, and implicitly in your mind, you'll need to immediately think about the positive side. So when I say false negative, it's actually a positive case. And you need to think in the line of the positive cases. This cell belongs to the row where all the positive cases are grouped. Some of these are, or hopefully majority of these are correctly predicted, which is false, true positive. But some of a portion of these are incorrectly classified and they lose the label P. They are classified as negative, so they are false negative. So over time, you will be used to making this adjustment in your mind. When you hear false negative, I'm talking about a positive case. When you hear false positive, it's a negative case. And this mentality is, well, because it's quite confusing, you know, as we talk about more terms, this mentality is useful. This confusion matrix, when the actual labels are on the rows or organized as the rows, most of the time, when we use those terms that we'll talk about, we refer to the term, the metric, with the context of the row, So either positive ground truth or negative ground truth. I'll talk about those when we get there. So I hope, okay, and it's a few more comments. Sometimes, a lot of times we need to divide a confusion matrix cell by some total. So there are three kinds of total here. There's a grand total, grand sum, which includes all four labels. When you add the four together, it's the total, which is the number of rows in the set. P refers to the number of positive ground truth cases, which is the row sum of the first row. And N is the total number of negative cases, ground truth, which is the the row sum of the second row. Make sense?
Professor Ma, quick question.
Yeah.
1 is positive, 0 is negative, right?
1 is positive, yes.
Okay.
Yes, yes. Good question. I said sometimes you see other layouts of table without you realizing it. And here is one example. We have predictions on the top, the same. We have actual on the left, but we have 0 and 1. 0 on the left or on the top, 1 at the bottom. Now, let's do something fun. So be sure that this layout is different from the one that you saw earlier. It's different. The columns and the rows are switched. Now try to tell me as fast as you can one of these is appropriate. True positive, false negative, false positive, and true negative. What's this?
True negative.
True negative, great. What's this?
False positive.
This is off diagonal.
False positive.
False. False positive. And why positive? Because prediction is the column. Column says it's positive, so it's positive. But when you hear false positive, it's talking about a negative case, where the row is referring to all the negative cases. Now what's this?
True positive.
True positive.
True positive, great, easy. And what's this?
False negative.
False negative.
Yeah.
Right, a little resistance there, right? Because our brain doesn't work that way very well at first. So again, things are different. The entire table, the 4 cells are completely flipped. Diagonal line, the 2 cells are flipped. They went like this, as before. And the 2 cells on the off diagonal line also flipped. If you compare this table to the one on the previous slides, everything changed. So with this change, it's hard to stick to the consistent interpretation, and takes more time to adjust to. So I would suggest that you stick to the same format whenever you see a new table, and you can arrange things, right? You can draw a table on the side and draw the layout that you're familiar with. In this case, this cell would go to here, and this cell will go there. And same thing, do the adjustment. But one thing remains, because the prediction is on the top and actual ground truth is on the side, and you have the diagonals remaining the same direction. It's not like this. So if this is 0 on the left, and actual label 0 is on the top, the diagonal line remain the same. But if you go like this completely changes, and it's too much to deal with. So better at least keep the diagonal line direction the same. Then the benefit of that is that, the 2 cells on the diagonal line, they are true. And depending on which one is positive and negative, it's a true positive, true negative. And off diagonal line is always false. Then you find a hint based on the prediction label. And you can quickly, realize which one is true, false negative, false positive. Good? All right, we will work with these terms in the next slides. Okay, so I'm throwing you six new terms that are different combinations or different calculations based on those labels that we talked about: false negative, false positive, false negative, true positive, false positive, and true negative. All are those sums that I talk about. P is this positive ground truth total, and negative ground truth total. Same thing here. So different things. You can always stick to the formula, which will give you the most accurate result. But it's like, checking the dictionary. If every time you have to check the dictionary, it takes a lot of time, and it doesn't really help you understand better. You can understand as much as the formula goes, but with a better routine, you can have a better understanding. And every time, when you want to calculate false negative, let's say, you think you in your mind you have a reflection of what that means, and then you can reconstruct, or you can you can almost memorize the formula, but not really. You can construct the formula based on your understanding. So let's do this. Let's examine these as the way they are formulated, and look and think about if that makes sense. The easiest one is accuracy. We have done accuracy so far. Accuracy has the total grand sum at the denominator, the total sample size. But on the numerator, we have two cells here. We have the diagonal lines. They are true predictions. They are correct predictions. The total of these two divided by the total number of rows, you have the accuracy. And the next easiest thing is the error. They have the same numerator. They have very different, they have the same denominator, have different numerators. And the numerator is entirely flipped. They have these two false predictions, right? And that makes sense because 1 minus error is the accuracy. Let's see, right? So they are complementary to each other. I can't even erase it. Okay, interesting. And let's look at the others. So let's look at this false negative rate, and then also look at true positive rate. False negative rate. It's talking about false negative, but out of what? Out of all the negative cases? No, it's actually out of all the positive cases. False negative is describing the errors that the algorithm makes in classifying all the positive cases. Of all the positive ground truth, how many did the algorithm incorrectly predict or classify as false, as negative, which is false? So you have the false negative on top, but you have all the positive cases, positive ground truth, as the normalizing factor at the denominator. So that's why I said, it better be get used to this routine or habit. Whenever we say false negative, it's actually referring to positives. So, and that's why the denominator is all the positive cases. Of all the positive cases, let's put it in the context. Let's say credit card default. So a false negative rate is measuring of all the credit card default customers, how many did the algorithm classify those default customers as non-default? So in a way, it failed to recognize or failed to detect the risk of the customer in terms of account default. So that's false negative rate. The flip side of false negative rate is true positive rate. Whenever you hear true, it's truthful. True positive rate is referring to the positive cases. You have the same denominator, but the numerator is true positive. Observe what is in the positive cases. Same here. Their order are switched just because of the different terms that we're calculating. The denominator has true positive and false negative. False negative is describing the positive cases, right? But it's incorrect classification. True positive and false negatives are the total positive ground truth. And same thing here, true positive and false negative. So the false negative rate has the false negative on top, but the true positive rate has the true positive on top. If you add them together, they become one. They are complementary to each other. So false negative rate and true positive rate are complementary. By the same logic, you will find that false positive rate and true negative rate, they are complementary as well. They share the same denominator. Their numerator is opposite to each other. So this is talking about the formula. Of course, this is accurate. You use these as a dictionary, you won't make a mistake. Otherwise, other than I guess silly mistakes, typos, but you can always be right. But it takes time, and it's not very efficient. So here's how I guess a lot of people understand it, or is able to retain it in their mind without remembering. I'm sure if you try to remember these formulas, it won't work. You will get confused. There are too many. The way that, so let's do it one more time. This time with different approach. Error. When we talk about, so let's talk about these in two groups. The first group is the error group. It describes the errors that the model makes. The second group is accuracy. It describes the correctness of the model. In terms of errors, of the four cells in the confusion matrix, is it the diagonal line or the off diagonal line that is describing the mistakes? It's the off. So, always remember this. The off diagonal line is describing false predictions. It has, the F as the leading character. It's false. Error is about false predictions of the model. So the immediate focus would be the off diagonal cells. Depending on which specific error you're talking about, you choose one of these, but it's always going to be one of these cells or together if you're calculating the total error. I'm referring to the numerator of these three different error terms. Make sense? Off diagonal line, off diagonal cells on the numerator of the error terms. Okay, so the next job is to understand what appears on the denominator. In terms of the error, it's all the cells, right? So visually, it will be easy to understand, as well as the formula itself is not very hard to remember, per se. Overall error is not the hardest part. So when you calculate error, it's the total of the off-diagonal cells divided by the total of 4 cells. That's it. That's error. Now here comes the harder part. Let's talk about false negative rate. What is it calculating in terms of the confusion matrix, or how can you use confusion matrix, smartly to make sure you calculate right without having to memorize the formula. Assuming that you organize a layout as such, where the predictions are on the top as columns, actual ground truths are rows, and you have the positive case column on the left and positive true label on the top. So diagonal line direction doesn't change. False negative rate, of course, should have the false negative on top, right? It should have the false negative on numerator. But when you hear false negative, you immediately think about positive cases. And the positive cases are the first row of the confusion matrix. So you should think of this box as the first row of the table. So false negative rate is calculating the percentage of the cell in blue out of the total of this row. So basically the first row. As soon as you understand, as soon as you identify the false negative cell, then you understand that this is about the positive case, which is the first row, and you have the false negative rate calculated correctly. Right. So in your mind, you should have these two boxes, and of course, the confusion matrix table. Now, for false positive rate, it's the same logic. So you probably know where I'm going. So in your mind, draw a box for how the denominator should be calculated. False positive is describing the negative cases. So it should be first row and second row. If it's row, and if it has to include that blue box, then there's only one answer, right? The second row. And it's a false positive, it's off diagonal cell, but the cell that corresponds to the negative cases or the positive predictions, right? So that's how it's calculated. So put these together for the error rates. Overall error, false negative rate, and false positive rate. Visually, these are how they are calculated, and it's easier to remember and make it less likely to make mistakes. So we'll move on to the accuracy. Same logic, but only just simply flipped the meaning. Accuracy is about correct or truthful predictions. So we are dealing with, on the numerator, we're dealing with the diagonal cells, no longer the off-diagonal cells. So for accuracy, we're talking about these two green cells, true positive and true negative. And denominator still is the entire sum, the grand sum of the 4 cells. Now, for true positive rate, it's talking about the positive cases. It has a true positive on the top, and the row sum on the bottom. The row sum should include the true positive cell. Then there's only one possibility here, the first cell, the first row again. the sum of the first row, which is the total number of true ground truths, and true positive on the top, you have true positive rate. True positive rate has other names. They are synonymous. You often, you see these names more often than true positive rate, maybe. Recall, sensitivity. So, some of the names have other nicknames. Some names don't have the nicknames. This makes another area of confusion. But, be used to it. That's the only thing I can say. Recall is also in the context of the ROC chart. Recall is on the y-axis. Sometimes also referred to sensitivity. But anyway, these three terms refer to the same thing. Moving on to the true negative rate, true negative on the top, and true negative is the bottom of the diagonal cell. Then to calculate true negative rate, you divide it by the row sum of the second row, right? So that's it. And true negative rate has another name, specificity, which is somewhat related to the x-axis of the ROC chart. We'll talk about that later. So by far, you have noticed that when we calculate the error, we use the row sum, the first row or the second row. By calculating accuracy, we also use that. So it seems that those terms have some internal relationships. And here you go. The two overall measure of the model, overall metric, which is error on the error side, accuracy on the truthful side, the sum is 1. False negative is describing the positive cases. False negative rate and true positive rate add up to 1 as well. And false positive rate, and true negative rate, they add up to 1. All right, have I really confused you?
I have a quick question. So
Yes.
how do we decide when evaluating the model if we should use the specificity or sensitivity?
It's a very good question. Usually you'll use several metrics to evaluate the problem. And because it becomes complex, you use several metrics until when you find the problem, or when you don't find the problem, that means the model is doing well. But we'll talk about the case later, in a few minutes, then they will apply these terms. So for now, it's mostly knowing how to quickly mentally construct one of these terms before we can talk about meaningful cases. All right, so let's do a let's do an exercise. Let's check the knowledge. I know that you perhaps are, maybe it's a total mess in your mind, or maybe not. I don't know. I may be surprised. So let's do some talking. Why don't you, so let's do some discussions here. Why don't you turn on your video and unmute yourself? So, brain check. Exercises make it better. Either you'll realize that really, I'm that good, great. Or really, I didn't get it. Think out loud or make it better. So let's try this. Without the visual cues here, but you can, let's see, I think you can draw on the board. Can you draw the board? I think you can. Let's see. So if it helps you, feel free to draw on the board. Yeah, you can do that. Great. So drawing boxes will be helpful, especially a box for the denominator. So so let's try. So I'll say a term here, one of these 6 terms, most likely these terms, the complex terms, and try to construct the concept in your mind in terms of how it's calculated by using the graph, the confusion matrix. And after you have thought clearly, you think you have, you're thinking clearly, then go ahead and say how it's calculated, or go ahead and draw. You can draw a small box and a large box. It will be clear what you're thinking about. Okay, ready? So let's see, false negative rate. So what's false negative rate? Anybody want to think aloud or draw on the screen?
It's true positive rate minus 1, or 1 minus the true positive rate.
1 minus?
Mm-hmm.
Okay, yeah, it's, but without knowing what the true positive rate is, how do you calculate the false negative, right? So, that's a way to get it, but each of these have its own way of constructing it by using the 4 cells. That would be the starting point, right? And this is simply to illustrate they're complementary. I think, I don't know who drew it. I can't see it now, but I think that is right. So false negative rate is talking about the error on the positive cases. It's the first row, right? As long as I identify the cell, at least, if it's diagonal or off diagonal, and I think you're on a great path. Now, another one, true positive rate. All right, good, great. The first row again. So true positive rate and false negative rate, they add up to 1 because they are both describing the positive cases. Okay, now let's do something more fun. Yeah, feel free to draw and practice. Now let's use words to describe what it means. And we need a context. Let's say fire. So the positive outcome is fire. Fire alarm detects fire. It detects smoke. It doesn't detect fire actually, but smoke is the result of fire. So the case is fire, positive outcome is fire, negative outcome is no fire. So explain what is a false positive rate. You would, so you need to think about what is a false positive. False positive rate. What's a false positive and what's a false positive rate? What is it measuring?
False positive is basically detecting fire even though when there's no fire.
Okay, right. So what is a false positive rate calculating?
So it's basically calculating, the rate at which it's detecting that fire falsely.
Right. Right. I think you're right. To elaborate more, it's calculating the proportion of false alarm
Yep.
out of what cases?
All
Out
the
of
cases?
false positive and true negative.
And these are no fire situations.
Yep, no fire situations.
Yeah.
Right. And do you know what is the, let's see, realistically, this cannot be calculated in, I guess, in real life, because we don't know this. Wait, hold on. We don't know this, right? Because the false alarm, the alarm constantly monitor the situation. So there's no, the true negative doesn't make sense. It doesn't, it's not an explicit test. So in the fire alarm case, this won't count. But if we change the context into something else, you want to name an example? I'm thinking about medical context. Something interesting. Okay, so let's say that's pregnant test. Positive case is pregnancy. Negative case is no pregnancy. So in this context, the same term, false positive rate. What is a false positive and what is the false positive rate describing?
False positive is basically detecting the pregnancy even though there's no pregnancy, even though a woman is not pregnant. And the false positive rate is telling you the rate, the rate of false positives in the no scenario. Basically in the scenario where the woman is not pregnant.
Right. In all across all the tests where the woman is not pregnant, what's the percentage of the false positive error?
Yep.
Right. And that's basically, it's describing the role sum. So, having this mental representation of the table and going with the rows helps a lot with understanding the rate, both the error rate as well as the truthful rate, right? So I think this is good exercise. I think you're on the good track. I think we can move on. Additional terms that are optional, but some of these are quite useful actually. So the terms that we talked about earlier is, in terms of those rates, we have true positive rate, true negative rate. We also have false, and same thing. And these are referring to the rate of error, or rate of accuracy. And they are according to the rows. We use the rows to normalize the measure. There are another set of terms which is describing the prediction status, I guess, and they go with the columns. So that's the mentality here. for the positive predictive value, negative predicted value, they are calculating the number of this is not error rate. These are correct predictions. These are more like prediction rates or predictive value. Positive predicted value is the amount of true positive of all the positive cases, even though some of those are false positive. So these are according to the columns. You identify the cell, positive predictive value is the true positive. Both of these are referring to the truthful cell. So either one of these. And true positive predictive rate is the true positive out of the bigger column. Yeah. So this is according to the columns. And these are useful in a different way. We'll talk about these, the value of, think about in this perspective in a particular case. So, and another nickname for PPV is a precision. You may have heard about it. So when you hear precision, it's talking about from the prediction point of view. It's talking about the positive predicted value. The other side is the negative predicted value. You identify the negative, the true negative out of the negative prediction column sum. And this one doesn't have a nickname. So these two are optional, even though many papers also refer to these. They are, I mean, the rate versus the value, they are useful in their own way. Sometimes we consider both, but for different purposes. We combine them because we don't want to lose any of them, or even though we prioritize one, but we don't want the other to completely fall off track. So we have a primary focus, but we use a secondary focus to make sure we don't miss anything totally. So that's the purpose. Now let's use this a different case. I think we have a bigger discussion as a large group, so we don't have to break up into smaller rooms. We'll talk about cancer detection. Same thing with pregnancy test, I guess, but different consequences. And one homework question asks you to analyze a case. The case will be different, but same logic. So here is the structure or the process that you answer those questions or think about. For every case, you think about what, and all of these are in binary classification framework. The first thing you will identify is the labels. What's a positive label, what's a negative label, or what's a positive and negative outcome. In cancer detection diagnosis example, the positive label is detected cancer, or presence of cancer cell, or bad tumor. The negative outcome is no tumor or benign tumor. Either way, it's no harm. And you would, at the population level, you would assume, and which is correct assumption, that positive cases is the vast minority of all the cases, because because testing is not expensive, but missing a diagnosis is very expensive. So out of abundant testing, the percentage of positive cases are very rare or very small, but not completely negligible. Positive cases arise when there is an actual cancer tumor, right? But the percentage is very low. Okay, so after clarifying the two labels, you would compare the two errors. There is a false positive error and false negative error. Interpret the error in the context of the case analysis and determine which error is severer, which error is more costly, in terms of money or in terms of whatever is valuable to life, right? So think about it. First, try to describe what a false positive error is and what a false negative error is in this case. So what's a false positive error here? Anybody wants to try?
Detecting the presence of a cancer when there is actually no cancer, that would be false positive, I guess.
That's false positive?
Yeah.
Mm-hmm. And a false negative?
When in the presence of a cancer, you detect it as no cancer.
Right. Or benign tumor.
Yeah.
Okay. Which one of these is severer?
I would say
false negative.
Yeah, false negative.
False negative is severer. Why? You describe the consequence of false negative, which means, what happens after a false negative, and what should have happened.
Was untreated, and health may prove fatal.
Well, if you have a false negative, that means that you would basically tell the patient that there's no tumor, the tumor is benign, and then they would actually need treatment over time and their condition would deteriorate, and then they would have no treatment, their cancer would progress if they had false negative.
Mm-hmm. Mm-hmm. Right. And what happens in the case of a false positive?
You would waste, they would have cancer, their tumor would be benign, and then you would be putting them under therapy or chemotherapy when they don't really need it. That costs a lot of money as well for them to get the treatment.
Anybody agrees or disagrees or has second opinion?
I think when it comes to false positive, the patient just have to go and get the test done and they will know if they have a cancer or not. So, but in false negative, even if they don't have cancer, even if they have cancer, it will be like no cancer. So the patient will not even go and get testing done.
Right. Put these all together. Let me try to restate. So in the case of a false negative, an actual cancer patient is told, based on the diagnosis, that there's no cancer. It's false negative, right? No cancer, but it's a wrong diagnosis. Because of commonality of let's see, negative diagnosis, meaning no cancer. Patient is not alarmed. Patient will presume life as if normal, while the patient is actually developing some cancer. So the patient missed a critical opportunity for treatment. And because cancer reproduces itself very fast, the patient may miss a critical opportunity to treat at early stages, right? Cancer will deteriorate quite fast. So the risk is life, or to the large part. So that's a false negative. And apparently this analysis would lead to the conclusion that false negative is severer, or should have been avoided, or should have more weights. In terms of false positive, what's the cost? The cost of a diagnosis, cost that the patient as well as the insurance company bears, or maybe the government, as well as the medical facility. But considering one case, the cost is fairly small. And typically with a positive diagnosis, even though it's a false, who knows? The first time, nobody knows. Patient will, or doctor will generally suggest a retest. And if the first test was a false positive, most likely the second test will be true negative. Make sense? So in this case, the cost is alert, which in fact is a false alert. It's alert and retests and confirm negative. So relatively smaller cost as compared to false negative. So your conclusion would be, false negative error is severer. And how do you reach that conclusion? You'll describe the consequences of both. I mean, first of all, the meaning of both errors, and imagine the realistic consequences of each of the error, given the error, or given the diagnosis, even though it's false, and compare these and to support, and they should support the conclusion that you make in terms of which error is severe. I hope this makes sense. We can do a lot of exercise that, but over time you'll find that it's following the same logic. So, but I think you have a good understanding by now. Any questions here? No? We move on? Great. Now, so additional model comparison. These metrics are mostly for model comparison. In model comparison, the difficulty is that every case is different. Every problem is different. So they differ by total number of cases. They differ by complexity, which is denoted by the number of parameter here. As well as, false negative versus false positive, which one is severer. Every case will have to involve some judgment. These factors make model comparison or model judgment very difficult. How good is accuracy score of 87%? How do you compare? How can you compare a false alarm or fire alarm case, fire alarm detector with a cancer detector? Is it a fair comparison? It's hard to say because technology is different, context very different, consequence very different. So some of the measures are robust to these factors. So then you can compare the same measure across two problems, and you can kind of see which model is good enough, which model has room for improvement, even though the context is different. F1 is one of these measures. Let me talk about the intuition here. F1 combines two concepts here, precision and recall. Think about what recall is. Recall is true positive rate. So think about that in your mind, the image. What is true positive rate? What's precision? Precision is positive predicted value. So this is according to the columns. If I draw it here, this is using the column mentality, and this is using the row mentality. So the question is why? Let's use, well, maybe we don't need a context here. For a model, imagine if you prioritize precision, which means the positive predictive value, which means of all the positive predictions, the percentage of those predictions that are true. So, you know, the percentage of the smaller box in a larger box. If the model performs very well naturally, that's good. But you can't always prevent the model will cheat, and model will learn that implicitly. What is a way that you can increase the PPV without really doing well? I can increase the true positive cell, of course. That's essentially improving the model. You know, increase the percentage of TP, true positive. But another way is to reduce right, to reduce this one as a shortcut without increasing true positive directly. A false positive case is where a false positive decision error is something related to negative outcome. And how do I reduce this? How do I reduce false positive? If I make zero positive prediction, zero, I only make negative predictions. In that case, if I don't have positive prediction, I won't have any false positives, right? False positive, let's see, when I have, right, when I have zero positive let's see, when I don't make any positive prediction, I will have zero false positive mistake. And the opposite side of that is I have perfect precision. But that won't work for a model to, in this case, any case where you have a binary classification, because in that case, the recall will suffer. What's recall? True positive rate is of all the positive ground truth. How many, or what's the percentage that you recognize? If you don't make any positive predictions, you won't pick up any of the positive ground truth because you will be only making negative predictions. So the way to cheat the system by increasing precision will, at the same time, will reduce or dramatically harm the recall. So that shows the benefits of looking at two metrics at the same time without blindly only focusing on one of the metric. So that's the case where if you want to, if the algorithm found a way to cheat the precision, it will reduce the recall. And if you analyze the other way around, if the model found a way to increase recall, it will lead to a poor precision as well. So using these two measures at the same time and somehow put them into one measure you can prevent the system from learning a shortcut, and will lead to truly a better model. So F1 score combines the two concepts together, and its value ranges between 0 and 1. And this is because if you have, in one case, if when the system wants to cheat, you have a perfect precision, but ends up having 0 recall, it will go to 0. And that's worst case. And the other way goes the same. If you increase recall by cheating, I mean, if the model increase recall by cheating, it will have a 0 precision. F1 score is still 0. But it's best if precision and recall are both 1. This is a perfect model, which doesn't exist. But assuming it does, then the numerator is 1 and times 2 as the weight, as a scaling factor, and 1 plus 1 is 2. Then 2 divided by 2 is 1. It's a perfect model by F1 score. So that's why in a lot of computations, F1 score is used as either the final evaluation metric to evaluate other sample predicted performance, or it's one of 2 measures. The other measure is the ROC AUC, which I'll talk about in shortly. This is obviously quite complex. It's more complex than the previous few slides, but I hope this makes sense. You can come back and review this. Let me go to the ROC curve and quickly talk about that. ROC, it's a long name. You don't have to remember it immediately, but the intuition is more important. The chart, don't try to read the chart if you don't know what's going on here. I have been confused 1,000 times before I understand how it works. So don't attempt. So here's the thing. ROC is a curve to describe how the model is doing in terms of predicting positive and negative cases. You can of course generalize the chart to multi-class prediction cases, but most likely the problem is binary classification. ROC curve is useful also because of the area under the curve measure of the model evaluation, which is one of the popular measures to be used to judge the competition winner. So the 3 lines here are 3 models being evaluated, and there's a 4th line, which is a diagonal line. And diagonal line goes this way instead of that way because the x-axis is on the bottom. So that's why. And this line refers to a baseline model. By baseline model, it is a model without any learning, which means it's by random guessing, coin tossing, or fortune telling without any evidence or any science. So if a model ends up being similar to the baseline model, the model is kind of useless. Any worthy model should perform much better than the baseline model, which is a random guess. The steeper the line, which is, if it deviates away from the diagonal line, if it goes like this, it's a very good model. If it's an arc, it's okay, but worse, if it's very close to the diagonal line, it's almost useless. But this is not the worst that you can go. You could have a model that is like this, or like that, which perhaps is because of giggle. You know, the data analyst doesn't know what he's doing or she's doing that will produce this kind of a model. ROC curve, the two axes here is the y-axis true positive rate, which is recall, TPR, it's over there, or recall. And the x-axis is false positive rate. False positive rate is talking about negative cases. It's about those mistakes that are made on the negative cases, right? And a lot of times you will see it's 1 minus specificity. We'll talk about specificity in a few. Right. Specificity is the true negative rate. So 1 minus true negative rate is false positive rate. But easier to remember is focusing on the P, but both of them are the rate. Y-axis is describing the true positive rate. X-axis is describing the false positive rate. So this way it's easier to remember. But the intuition, you know, what is this line doing here? And why is this line a baseline? You know, this line being the baseline, it's a critical point. If you understand this part, you can go beyond that and be able to understand a better model. Why is this a better model? And why is this the best model if it's like a triangle? Okay, so what the ROC curve is doing, or how is it constructed, is the calculation varies the threshold in the binary classification problem. So assume that this is the activated value of the output neuron in the case of a logistic regression, I guess. So when you have an activated value of the output neuron, you have a number, you know, it goes from negative infinity to positive infinity, but most likely between -2 and +2. Hold on. If it's activated value, it should be bounded between 0 and 1. My bad. And typically we use a threshold of 0.5 in logistic regression case to as a threshold to make classifications. So the way the line is produced is that it changes the threshold, hypothetical threshold, from the highest value to the lowest value, and record the false positive and true positive and false positive rate at those hypothetical threshold values, and draw a line here. And this line turns out to be very useful. So let's try to understand why the diagonal line of the AUC is 0.5, which is the area under the curve, out of the entire square is 0.5. That describes how the model is doing. What does this 0.5 mean? And why is this a random gas? So the AUC, or let's see, the AUC is describing the probability that if you randomly pick 2 cases from the data set, if you randomly pick two cases, and what is the probability that the true predicted score of 1 point is, or the probability that the probability that the actual positive case has a higher predicted score than the actual negative case. So you randomly pick 1 point from the positive ground truth case and 1 point from the negative ground truth case. What is the likelihood that the model will predict correctly, will rank them correctly? That's what the AUC is doing. So by a random guess model, it does nothing. It simply flips a coin. So in that case, if you randomly pick a positive case and randomly pick a negative case, there's 50% chance that the model, a random guess model, will order them or will predict them correctly, will order them correctly, because random chance, the true order and the wrong order is equally likely. So that's why the baseline model is 0.5. And how to understand this chart? This chart is actually visualizing, where the point is actually. So let's pick, let's say this is a logistic regression case, and we use a threshold of 0.5 to make classifications based on the activated value. So in this case, the threshold of 0.5 is the almost the middle point of one of these lines. Let's use the black line here, one of these. And the point here is in the middle. So it has a true positive rate of close to 0.6, and it has a false positive rate of close to 0.45, maybe 0.45. And what does this mean? This line here is visualizing the threshold, and you have two distribution here. The red color indicates all the positive ground truth, including those here that has a lighter color. The red color, as well as the direction of the stripes, indicates the positive cases, and the blue stripes that goes this way represent the negative cases, and those are ground truth. When the color is dark, that means it's true prediction. So dark red is true positive, and dark blue is true negative. When the color is light, it's false prediction. So positive cases predicted as negative because it's below the threshold. It's false negative. It's actually positive cases. And light blue is false positive. It's actually negative cases. So by drawing the line here, you have true positive rate is true positive divided by true positive predicted right is here. This part divided by everything under this distribution. You can see that it's a majority, so 60%. This is not, very specifically mapping with the distribution here, but it's close. So majority cases are among the positive cases, which is under this red curve, is correctly predicted as positive. So that's true positive rate. That's that. You have slightly lower than 0.5 false positive rate. And what's false positive rate? It's describing the negatives. So false positive is light blue, is here. Light blue, the percentage of the light blue out of all the cases under the blue curve. So that's the false positive rate. Out of all the negatives, how many is predicted as positive incorrectly? That's that. So you see that this is a minority, maybe below 40%, but this line is close. So that's how every point on these lines are calculated. And once you have all the dots, you connect those, a curve is constructed. And the curve is constructed by varying the threshold level. So what does this point mean? This point has 0 true positive value and 0 true positive rate and 0 false positive rate. This is when the threshold value is way up. When you choose the threshold value equal to 1, let's say, everything will be predicted as negative cases because they all fall below the threshold. If you have 0 positive prediction, you make all the negative predictions. You will have 0 true positive rate because you don't make any positive prediction. And you will also have 0 false positive rate. You have 0 positive prediction by the same token. So both of these are 0. And that's for every model, that's a case. Where is this line here? When you have true positive rate of 1, you will also definitely have a false positive rate of 1. This is when the threshold line is moved to the left end. When you make everything positive, when you predict everything positive, and there's no negative cases. So in this case, all the positive cases under the red curve are correctly predicted, and they are the basis for the true positive rate of 100%. True positive rate is how many of the positive cases are predicted correctly as positive. It's everything, but you have 0 true negative rate because everything under blue is also predicted as positive where they are actually negative. If you have 0 true negative rate, then you have the other side, 1 false positive rate, which is this line here. So the line, however it curves, it will end up in these 2 points at the extreme. But everything in the middle, it could change depending on how the model behaves or how the model is doing well. So I hope this makes sense. It take a long time to rationalize it, but I think this is a good point to start. Any questions? I think I'm going overtime. Anyway, any questions? So here the AUC area under the curve is referring to ROC curve. Different scenarios. If we have a perfect model, you have AUC of 1 or 100%. It's kind of a square turn here. If you have more typically, you have a curve, a concave curve. It has AUC of, I think a lot of times cross-validation AUC of 0.5 or above is good in terms of binary classifications. When the curve aligns with the diagonal line, this is a baseline model. It has AUC of 0.5, which is a random guess model. You could even have AUC of 0, which is I mean, not even a model, I guess it doesn't belong here. So, be sure to recognize what is considered a good model and what is considered not a good model based on AUC. Advantage of AUC, it's robust to imbalanced data set, imbalanced labels. You can compare AUC even when your problem faces the imbalanced label problem. It's also insensitive to the arbitrary scale of the output values of the model. So you can compare the results from neural networks with logistic regression. They may, because of different activation units or activation functions, they may have slightly different scales in terms of output activated value, but you can use AUC to compare those different models. This is what actually it means. It takes a while to understand it, but if you, find it hard to understand it, I can help you. And I think I'll skip the hands-on here, but you can look at the slides. I mean, not slides. You can look at the Jupyter Notebook. Here, I use the scikit-learn package to replicate calculations of 5 metrics. Not everything you can find a direct function, but with additional effort, when you minus something from one, you get another thing. So that's another indirect way to get those other measures. Here, I only demonstrate those measures that you can directly get. You can get accuracy that you are already familiar with. You can get recall sensitivity or true positive rate based on the recall score from scikit-learn. You can get false positive rate not by using 1 minus TPR. 1 minus TPR is not FPR, so remember that. 1 minus TPR is FNR, false negative rate. So be careful. But you can get false positive rate by using the ROC curve function, because ROC curve basically uses 2 measures and produces 2 measures. It produces the true positive rate and it produces the false positive rate. So you can get the false positive rate by using the ROC curve function. You can get precision, positive predicted value by using the precision score. You can get the F1 score by using the F1 score function. So you can get these 5 fairly quickly from using the scikit-learn. For some of the other terms, you can use 1 minus technique to calculate those fairly easily. For the rest of it, you probably have to calculate by hand. I illustrate 2 ways in calculating each of these measures by hand, using formula by hand to calculate the hand calculate version, and using programming to calculate that and compare the values. They are the same across all the values, as long as you calculate it by hand correctly. To do this demo, I had to construct a hypothetical data set which contains the true label as well as the predicted label of the data. And I'm using the values here shown in the confusion matrix as the 4 elements. And I use these 4 to construct the fake data. You'll feel free to take a look if you want to learn how I did that. Feel free. If you have any questions, let me know. I can explain those codes for you. When I make the video, I'll most likely also include some of these there. I will I'll elaborate some of those techniques, for the sake of understanding this. All right, I guess that's it for today. We'll open this up for final questions. I think you probably don't have many homework 3 questions, but just in case you have new questions, we can do those. Yeah, questions? Any questions?
Professor Ma, this is only for the categorical variable, I mean the target variable which has 2 attributes, right? Not for multiple attribute, multiple categories, sorry.
Some of these can be generalized, but there are additional things to take care of. So it's not direct generalization, but some of them can be used over there.
Okay.
Yeah. With the binary classification, it's the most directly useful.
Okay, thank you.
Mm-hmm. Any other questions? How do you draw on slide? Wait, okay. Use anything. Right. Any other questions?
Professor Ma,
Yeah.
I have a question. So, how to draw the correlation plot for categorical variables?
I'm afraid. I mean, wait, hold on. Correlation line? You mean the scatter plot? Regression lines?
Like the heat map.
Heat map. I think this is related to one of the homework questions, right?
Yes, but in the homework we are only asked to draw the
right. That's one of the things.
Numeric variables.
Right. I only asked you. So, and I think this says a lot. Basically, there's no good ways to. There's no good way to incorporate categorical variable in the heat map. In terms of correlation, you could, of course, you can convert them to dummy variables. So a categorical variable will occupy several rows in the heat map as well as the columns, right? Because it's a matrix. So you'll have to make additional notation to indicate that these 3 rows as well as these 3 columns, they are from the same categorical variable. So it's kind of hard to do that with clarity. So in many cases, we don't include the categorical variable in correlation analyses.
Okay, so it would be better if we transform them into dummy variables.
Right. And in most cases, if the categorical variable has more than 3 categories, you are not very likely to find high correlation, even if you convert it to dummy variables. Because in the case of dummy variables, each of the dummy does not carry the entire information from the categorical variable. So the heat map, the correlation chart is not telling everything by each of the cell. So I guess that's another reason we don't include those. And we typically don't detect very high correlations. It's when you consider them together as a group, its correlation with the target might be high, but it's arbitrary. You know, the class labels don't have order. So that's all the difficulties with categorical variables in correlation chart.
Got it. Thank you.
Yeah. In case of dummy variable is a special case of categorical. It typically doesn't require transformation. A lot of them are coded as 0, 1. In that case, the interpretation of correlation is the same as if the dummy variable is a continuous variable, because it only occupies one row and one column. So when the two labels have correlation with other variables, the correlation value, the meaning is the same.
Yeah, actually, I asked this question because in exam 1, there's a question that asks us to show the correlation between all the variables, including the categorical variable. So
It does?
that's why, yeah.
I'll check that. Great, thanks. Any other questions? So if there's no question, then we can call it a day today. Have a great night. Enjoy your comfortable, your comfy blanket, I guess. I'll see you next week. Email me if you have any questions about the homework.
Professor Ma, I have a question.
Yeah. Okay.
I'm sorry. Sir, the question is, imagine I'm working on a neural network model,
Right.
and I want to know which of my predictors are really influencing my target variable a lot. Do I look at the weights? I mean, does weights help me determine this?
Ultimately, it's a weight, but it's a combination of weights, and many weights go into, go into the interpretation of one variable. So tracing the weights will probably not be a worthy homework to do. So I think a good starting point is at least you narrow your focus to a few variables, and that's when you can use maybe boosting based models, or maybe lasso, to kind of identify a short list of variables to focus on. And then you can use sensitivity analysis to, change the levels of one variable while holding all the other variables constant. Then you can kind of, get a sense of how sensitive the model is to that variable.
Right. So I was also thinking I can look at the weights of my last approach.
Not really. How can you be sure which weight is influenced by a particular variable? If you have more layers, right? So think of the first layer, the first hidden layer matrix, perhaps is the best way that you can differentiate the variables, because the connection between an input and a specific hidden unit is very clear. But after you go through several hidden layers, it's hard to trace back, which variable is making. Yeah. But even though it's clear in the first layer, you need to know that the first hidden layer usually have very small values. So the coefficient size is very small as compared to the last layer. So it adds another difficulty to differentiate. All the values look like very small. How do you tell? There's no standard way to surface any kind of significant values. Yeah.
So I have one more question, sir. I don't know if this makes sense, but do we, by chance, in any situation, combine multiple models to make our classification prediction better?
Oh yeah. Random forests is combining different trees. There are fancier ways to combine them.
Right.
I didn't work with many different kinds of models, but the basic idea is that you can reduce the sensitivity of or you can increase the reliability of your overall classification by using many of the small trees. This is similar to the idea of gradient descent. Every tree captures something significant there, but alone cannot be trusted. So you combine different trees together and the results are much more reliable. In terms of neural network, well, before I talk about neural network, there's another technique called second opinion, kind of, the idea is very simple. If the model suffers from one kind of error, if the model suffers from high false positive error, too much negatives are classified as positive.
Right.
In that case, one model alone is not able to I guess avoid the error. So you train two very different models, a logistic regression and a decision tree. The two models are very different. They have different mechanisms of being either liable by the bias or maybe immune to the bias. So you train both models and make prediction using both models, but you only predict positive if both models predict positive. So this is a second opinion kind of approach. So that way you can reduce false positive by a great amount. Instead of adjusting the weight, the threshold, you never adjust the threshold as we talked about last time, right?
Right. So random forest is it a part of decision trees, sir?
Yeah, the basis is trees, but it modifies how each the tree is able to be trained. I think random forests or boosting, maybe the boosting model is by training each tree based on randomly disabling some of the input variables. So, but this is all random process. So every tree is limited to use only 3 of the variables. And the way they limit the 3 variables is by, stochastic process. So in this case, each of the tree has only a limited data set to work with. Somehow, all these trees will converge to a good result for some reason. I don't know the very specifics of that, but what I know is the boosting as well as for the random forest is quite good before deep learning becomes popular.
Sure, sir. Got it, sir. Thanks a lot.
It's very interesting. You can look into it.
Yes, sir. I will. Thank you so much.
Yeah, sure. I guess that's it. We'll good night, and we'll finish this meeting. Yeah, enjoy the night.